Good morning. My name is Abdulaziz, and today I'm presenting my business database system project titled Database Management System Development for Smart City Infrastructure Management. Over the next 10 minutes, I will demonstrate how database management systems serve as the foundational infrastructure, enabling modern smart cities to transform vast amounts of sensor data into actionable insights that improve not only the quality of life for millions of citizens, but provides very actionable insight. This presentation will cover the essential components of database management architecture, the systematic database design methodology applied for smart city scenarios, and the quantifiable benefits, including 40% faster emergency response times and 30 to 50% operational cost reduction. Let's begin. First, let me establish what a database management system actually is and why it's absolutely critical for a smart city operation. A database management system is a sophisticated software serving as an intermediary between users and databases. It provides a centralized repository for systematic data management. In business context, database management system serves three core purposes. The first purpose is systematic creation, retrieval, and management of data. The second core purpose is to ensure data integrity, security, and consistency. And the third purpose is enabling multi-user concurrent access with ACID properties. ACID standing for atomicity, consistency, isolation, and durability. These properties ensure that even when hundreds of users, for instance, are simultaneously querying the database, the system maintains reliable and provides correct data to the users. Now, why do smart cities specifically require robust database management solutions? Smart cities generate vast amounts of data. We're talking about millions of sensors reading daily from traffic monitoring system, environmental sensors, public transit GPS, citizen service platforms. So this creates what we call very high velocity, high volume, and heterogeneous data, also known as big data. Without the database management system, this data would remain siloed into disconnected systems. So traffic data wouldn't correlate with environmental data, for instance. Transit operation wouldn't integrate with citizen services requests. And the database management system is basically what will enable cross-domain analytics, meaning that we can see trends by comparing data coming from different sources. So for example, in Singapore, a smart city infrastructure manages data from over 110,000 sensors through a centralized database management system, enabling real-time monitoring, but also predictive analytics across the entire city-state. So the smart city scenario I've designed integrates four primary infrastructure domains. Let me walk you through each of them. First domain is traffic management. So when we talk about those, we're talking about loop detectors embedded in roads that count vehicles, traffic cameras with image recognition, for instance. For a mid-sized city, we are looking at millions of traffic readings being inserted into the database every single day. The second domain is public transportation network. So this encompasses GPS tracking for every bus and metro vehicle, automated passenger counting at system doors, fare car transactions, and route schedule, for instance. Requiring the database to handle thousands of update operations, meaning that not only we are storing the data, but this is being updated on a timely basis. The third domain is environmental monitoring infrastructure. So this includes monitoring air quality, using sensors such as PM2.5, PM10, monitoring nitrogen dioxide, ozone, and carbon monoxide concentration. It also includes noise level monitors, weather stations, tracking temperatures, for instance. These readings are captured every 5 to 15 minutes. And they are creating a continuous time series data that can be correlated with other sources such as traffic patterns, which can then allow to understand how congestion impacts air quality, for instance. So the fourth domain is municipal services. So here we're talking about waste management with smart bins that signal when full, water and energy distribution, for instance. Public safety incident reporting and citizen engagement portals where residents can submit, let's say, requests and track resolution status live. So now, as you can see on the right side of the slide, these integrated domains deliver proven benefits. For instance, the Barcelona Smart City implementation achieved a 40% faster emergency response time by integrating traffic, safety, and dispatch systems. Amsterdam also reduced operational costs by 30 to up to 50% through data-driven resource optimization across waste collection, energy, and also public services. Moving to the next slide, let me break down the specific data requirements and challenges for each domain. So for the first domain, we are capturing vehicle count, speeds, occupancy rates, and GPS coordinates. For Kuala Lumpur, with over 2,000 traffic sensors, this generates 5 to 10 million records daily. The database must then be optimized for high velocity while still supporting real-time analytic queries. We also have for environmental metrics, air quality sensors, and all those. We create a time series data requiring specialized storage, like table partitioning by data ranges to maintain query performance as historical data keeps on accumulating with time. For transit operational data, the challenge is balancing write performance for continuous update with read performance for passenger-facing arrival predictions. And the fundamental challenge is mainly managing data that is simultaneously high volume and high velocity with diverse types requiring different type of processing strategies while maintaining strict security and also enabling real-time analytics, for instance. This is precisely why smart cities require enterprise-grade database management systems rather than simple file-based storage. So now we'll be discussing the essential database management component. A production-grade system consists of 5 essential components. The database engine, which has a core storage retrieval with MVCC for concurrent access, the query processor, which optimizes complex queries joining traffic, environment, transit data. Then we also have the transaction manager, which ensures the ACID properties for data integrity. And we have the security manager, which ensures the role-based access control, encryption, and also audit logging. And finally, we have the backup and recovery. This is very important as it allows, in case there's a crash in the system, to recover a previous version without necessarily losing the data or the systems that have been in place. Okay, now let's talk about the design methodology for our database. Designing a smart city database follows a systemic 3-phase methodology. Phase 1 is ER modeling. That's entity relationship modeling. We identify the core entities, which here are sensor, citizens, vehicle, and so on. For each entity, we then need to identify its attributes. For example, a sensor entity has sensor ID, sensor type, latitude, longitude, and so on. Each sensor generates, then we establish the relationships. Like each sensor generates many traffic readings, right? That's a one-to-many relationship. And each citizen can submit many service requests, another one-to-many relationship. The ER diagram visually maps 3 relationships to ensure we have captured all the data dependencies. Phase 2 is normalization. So normalization is to eliminate data redundancy through 3 levels. First, normal form requires atomic values. So if a citizen has multiple phone numbers, we don't store them as a comma-separated list. We create separate rows in a related citizen phone table. Second normal form removes particle dependency. For instance, if we have a composite key of a driver and a trip ID, the driver's name depends only on driver ID, not the full composite key. So we separate driver details into a driver table. Phase 3 is key identification. So primary keys like sensor ID and citizen ID uniquely identify each record. Foreign keys enforce referential integrity. For example, the sensor ID in the traffic reading table must match an existing sensor ID in the sensor table, preventing orphan data. For time series data, for instance, we often use composite keys like sensor ID plus a timestamp to uniquely identify each reading in the database. The result of this methodology is an efficient schema with a minimal redundancy, guaranteed data consistency through constraints, and a scalable design that accommodates for future growth. So now let's talk a little bit about the SQL operation. So SQL provides standardized interface for all database interactions. Let me illustrate the 4 core operations we have. So we have insert. Insert allows to capture real-time sensor readings. For instance, millions of traffic readings daily from 1,000 plus sensors. Updates allows to refresh vehicle location every 10 to 30 seconds by enabling real-time passenger arrival prediction. Delete operations manage the data lifecycle. We don't keep raw sensor data indefinitely, so that would consume massive storage. Instead of that, after like 90 days, we first copy detailed readings to an archive table for compliance purposes, then delete them for the active table. Select operation provides analytics and insight. This is where the real value starts of emerging and we start to manipulate the data. We can execute complex queries that can correlate with like traffic congestion levels, with air quality measurements, and joining traffic reading table with the environmental reading table based on the average for pollution level, for instance. So these are some SQL operations we can do that can actually make the data really malleable and usable. Now let's talk about the 3-tier report architecture. So effective smart city governance requires tailored reports for different audiences. I've identified mainly 3-tier reporting architecture. So first we have operational reports. So this is about real-time dashboard refreshing every 30 to 60 seconds. So traffic congestion, heat maps, transit status, and environmental alerts. Second is analytical reports, so monthly, quarterly performance analysis. This could include route optimization, traffic flow patterns, and also service quality metrics. And finally, strategic reports. So this will be related to everything that's executive KPI scorecard. So our cost benefits analysis, CPA, sustainability metrics, and also the investment planning. Are we on track based on the finances that we're targeting? So let me quantify the transformative impact of smart city database management implementation through Pro Metrics. First benefit, operational cost reduction. The operational cost is reduced on average 30 to 40%. This is due to smart waste collection and also things like adaptive lighting. And daily commute reduction from 15 and up to 20 minutes, which allows for optimized traffic management. The other key benefit we also see is 20 to 30% reduction in emission reduction. This could directly correlates to traffic environment friendliness. And finally, 85 to 95% of service resolution rate. So this system allows to actually handle customers' queries way faster than it would usually take. So in conclusion, the first takeaway is that database management system is an essential foundation for smart city viability. It's not an optional technology per se. It's core infrastructure. Just like roads and utilities, it allows to transform raw data into actionable wisdom. The second takeaway is integration creates exponential value. The benefits I described are cost reduction, time savings, and also emission reduction. And the third key takeaway is the return on investment that is quite compelling. Initial implementation for mid-size range from 10 to $10 million, but through operational cost savings, the return on investment is quite fast. So looking forward, the evolution continues. Machine learning now enables predictive analytics, forecasting congestion and infrastructure failures before they actually occur. So that's it for my presentation on business database management. Thank you very much.